Hi, this is Shiva. In this video, I'm going to talk about convolution neural networks or ConNets. We're going to describe this picture later in this video, but I'm going to start off with history of convolution neural networks and then going to the math piece and then taking by example. Convolution neural networks are perhaps the greatest success stories of AI inspired from neuroscience. The history goes way back to 1960s by the experiments conducted by famous neurophysicists Hubel and Wiesel. They try to understand how the mammalian brain works and then reveal lot of fundamentals that are very much important for present state of the art deep learning techniques, like understanding the primary visual cortex and how the mammalian brain learns through different layers, abstracting information in different layers like simple cells, complex, and grandmother cells. So then it was successfully implemented by Jan LeCun in 1998 by detecting handwritten characters, which is famously used in reading checks. Later in with the recent data and cloud exposure, like CNNs became very popular with the AlexNet, which is used in the ImageNet competition in 2012, where it opened doors for a lot of research and innovations in deep learning. Uh, CNNs are a specialized neural networks that operates an operation called convolution, at least in one of the layers. Convolution is an operation on two functions of a real valued argument. If you take a two-dimensional input, we can return the convolution operation as below, like where I is your input image and k is a kernel, and it just you just do a element-wise multiplication and sum over all the channels. That's what the operation is doing, and sometimes the output of this convolution is referred to as a feature map. However, in all of the in most of the machine learning libraries, an equivalent function of convolution, which is called cross correlation, is implemented, uh, uh, which where it's just simply a convolution operation, but without kernel flipping. Let's take an example of this. Like as you can see on the screen, we have a 3 by 4 shaped input and then 2 by 2 kernel, and we are doing element wise multiplication and summing them all through that patch. You can see the first cell, like a is multiplied with w, and then we add that with b into x plus e into y and f into z. So this will be the output after applying convolution on this input. You get a 2 by 3 matrix as an output. So there are a few important details that made convolution networks very popular and efficient. One is sparse connectivity. Like as you can see in this image, your when you apply a kernel, which is also called filter or weight matrix, on a patch of an image, you do convolution and then you generate that output into the which will be input to the next layers in the network. So this field like this field highlighted in the blue is called receptive field, and as you can see, only these fields, these values of these pixels or inputs are responsible for changing the value or affecting the value in the single element of this output. So we don't have to do entire matrix multiplication on the entire image to get the value. Because of this sparse connectivity, we get a lot of computational efficiencies, and our learning process happens pretty much faster, and we'll not going to our computations will not explode. The other one is parameter sharing, like the kernel weights, like whatever we have will be used for the same the same parameters in the kernel will be used across the different patches of the images, so we don't have to learn different parameters at different patches of the image, though we have multiple kernels that abstracts or captures different features automatically during our training process. And then equivariant representation, that's another thing where it our network basically convolution neural networks will try to capture or give the same output even if there is a small change in the input. uh, Other things we need to consider, we need to take care in the connet is like assigning the initial weights or initial values for these kernels. There are multiple ways. One is like you can randomly assign values for these kernels from a known population distribution. Otherwise you can apply handcrafted features based on your domain knowledge, or otherwise apply incorporate some unsupervised learning techniques like k-means algorithm. Like you can apply k-means on this specific patch of the image and take the centroid and use that as a use that as the initial weight of the kernel position. And once you train the convolutional neural networks after this assigning the initial values, and then you pass through the next layers of the connet of the neural network, and at the end like you calculate a loss function, and then you back propagate the loss or the gradients at different levels, adjusting the weights of these kernels. So that's what the learning process. Once you train the convolutional neural networks, these parameters will be learned with the nature of the data and the problem that we're going to solve uh, with the objective function that we define. Uh, typically a convolutional neural network contains three different stages. One is like a layer that performs several convolutional operations in parallel to produce set of linear activations, and then these set of linear activations are run through a nonlinear activation function such as ReLU or something to condense the values, and then to have a sparse values in our matrix, like having zeros in most of the places, and otherwise you'll have weights which actually captures a specific feature which is relevant to the problem that we're going to solve. And then the third stage is applying a pooling function which modifies the output of the layer by taking a summary statistics of the receptive field, or the pooling function width and I mean shape that we are defining in our network. There are different sorts of pooling functions like max pooling, average pooling. Out of being, max pooling is popularly used. And as a nonlinear activation, ReLU is generally used as a nonlinear activation. Uh, that's it pretty much from this video. Thank you.